All right, let's get right into it. Today, we're going to unravel a scientific detective story that is absolutely essential for your board exams: the structure of the atom. We're going to follow the clues, piece by piece, that took us from just a vague idea to a revolutionary picture of matter itself. Okay, so let's set the scene. By the end of the 19th century, scientists had a few key facts. They knew atoms existed, they knew atoms were electrically neutral, and they knew they had these tiny, negatively charged things inside called electrons. The million-dollar question was, how in the world were all these pieces put together?
So where does our story begin? Well, it starts with the first major clue, the first real attempt at a model. And it was proposed by the guy who discovered the electron himself, J.J. Thomson, way back in 1898.
This model made a ton of sense at the time. It was simple and it perfectly explained why atoms were neutral. You've got this positively charged pudding that perfectly balances out the negative little plums scattered inside. It was a solid first draft. But like in any good detective story, a new piece of evidence was about to blow the case wide open. Okay, this is where things get really interesting. The next chapter is written by Ernst Rutherford, who is actually a former student of Thomson's. He came up with a truly groundbreaking experiment carried out by his associates Geiger and Marsden, specifically to test that plum pudding model. The idea was just brilliant in its simplicity. Fire these tiny, positively charged bullets, called alpha particles, at the atomic pudding. Now, if the positive charge was all spread out like Thomson thought, those alpha particles should just zip right through, maybe getting nudged a tiny bit. Think of it like firing a BB gun through a giant block of Jell-O. No big deal, right? Well, the results were not just different, they were absolutely mind-blowing. Sure, most of the alpha particles did pass straight through, just like they expected. But some were deflected at huge angles, and a tiny fraction actually bounced almost straight back. What could possibly be happening? This was just a stunning result. Rutherford famously said it was as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. I mean, can you imagine? The main takeaway here was undeniable. The plum pudding model had to be wrong. Completely wrong. That Jell-O had to have something incredibly hard and tiny hidden deep inside.
So based on this incredible, totally unexpected data, Rutherford tossed out the old model and proposed a revolutionary new one. He'd found the atom's secret.
This new nuclear model was just brilliant. That tiny, dense, positive nucleus explains those rare but massive deflections. The huge amount of empty space around it explained why most particles pass through untouched. And the orbiting electrons accounted for the atom's size and neutrality. But here's the twist. In solving one mystery, Rutherford had created an even bigger one. And this, right here, reveals a massive problem. See, an electron orbiting a nucleus is constantly changing direction. That means it's constantly accelerating. And according to all the laws of physics that everyone knew at the time, any accelerating charge should radiate away energy. This meant the electron should lose energy, spiral inwards, and crash into the nucleus in a fraction of a second. So our detective story has hit a major wall. Rutherford's model was perfect for explaining the scattering experiment, but it completely failed to explain two fundamental facts about our reality. First, why atoms are stable and, exist at all. And second, why they produce these sharp, distinct lines of color instead of a continuous rainbow of light. The case needed a new detective, one with a really radical idea. And then, in 1913, the Danish physicist Niels Bohr steps onto the scene. He made a really bold claim. He said the old rules of classical physics, the rules of our big, everyday world, they just don't work at the atomic scale. So he proposed 3 revolutionary new rules, or postulates, to rescue the atomic model.
Bohr's first move was just audacious. He simply declared that there are special, stable orbits where electrons do not radiate energy. This went against everything classical physics predicted. He basically said, look, atoms are stable because they just are, and here's the new rule that says so. This was one of the first shots of the quantum revolution.
Now, this is the mathematical heart of his model. He said that orbits aren't just anywhere, they're quantized. To make that simple, think about a set of stairs. An electron can be on step 1, or step 2, or step 3, but it can never just flow in between on step 1.5. This rule meant that only very specific orbits at specific distances and with specific energy levels were allowed, and this is the key that finally unlocks the mystery of those line spectra. And this just brilliantly illustrates the solution. Those distinct lines of color we see in an atom spectrum, they're basically the fingerprints of these quantum leaps down the staircase. Each and every line corresponds to a specific jump an electron makes between two of those allowed energy levels. A big jump from a high step to a low one releases a high-energy blue photon. A smaller jump releases a lower-energy red photon. It's that simple. So it seems like the case is solved. Bohr's strange new rules, this mix of old ideas and wild quantum hypotheses, they seem to explain everything. But the real question is, how well did the theory actually match the evidence? Let's move on and see how it really stacks up. For the simplest atom of all, hydrogen, Bohr's model was a spectacular success. A home run. It explained why it was stable, it predicted every single line in its spectrum with unbelievable precision, and it calculated the energy needed to rip its electron away. For your exams, it's absolutely crucial you remember these major successes. But, and this is a really big but, the mystery wasn't completely solved. The moment scientists tried to apply this model to any atom with more than one electron, like helium, it completely fell apart. It was this beautiful, elegant theory that only worked in one very specific case. And this shows us that Bohr's model, while totally revolutionary, wasn't the final answer. It was, however, an absolutely essential stepping stone that proved the quantum world was real. The full story, of course, would continue with the development of modern quantum mechanics, which replaced Bohr's simple orbits with fuzzy clouds of probability. But his flawed masterpiece was that essential first step. It proved, beyond a doubt, that the universe, at its smallest, most fundamental scale, plays by a completely different and much, much stranger set of rules. And that really leaves you wondering, what other rules of our world are just waiting to be broken?